So this is properties of a stretched string. This is a supplement to the material in section 4.3. So just to remind you, we're looking at a stretched string here that's connected. It's a string that's connected on two ends where we're assuming the ends aren't moving. So this is a horizontal, I can't draw so well. And there's a little bit of tension in the string. And now we imagine, for example, that you pluck this string and then we want to now think about what happens. That's a terrible drawing. Think about what happens. You pluck the string and the string starts vibrating. So certain assumptions, we're assuming that the motion of a point on the string will move directly vertically. That's not entirely true. There's some arcing as the string bends. And also for small vibrations, we assume that the change in the length of the string is negligible. From what I understand, this vibrating string is essentially a spring now, and there's going to be some stretching of the actual string. So it's the combination of the tensile forces, the tension, gravity, initial position, and velocity that cause this vibration in time, at least according to our model. And so in our PDE, the vertical position U is what, is the unknown, is what we're looking for. And so, think of a musical instrument such as a guitar or a violin, and you have the string, when it's not being touched, is in a, sort of equilibrium position. Here we think of it as being horizontal equilibrium position. And then maybe if you're going to pluck it, so maybe this is plucking the string, pulling it up, maybe with a pick, and then you're going to let it go and let the string vibrate. And now we kind of want to analyze this behavior of the vibrating string. So in particular, we want to connect up today some of the physical implications of the model. And so our model has taken into account the material that the string is, by using density, the thickness of the string. The model incorporates cross-sectional area. Of course, the vertical displacement is the center of the model. And the horizontal tensile force, the tension, that's also part of our model because, our string is tied. And so with the tied ends of the string, mathematically, that gives us a boundary condition. So from a PDE point of view, we should interpret this. These are boundary conditions. From a physical point of view, it says the string at the left end is at a fixed height of 0, and the right end of the string is at a fixed vertical height of 0. And now, there could be external forces which we'll incorporate in our model due to gravity or a guitar pick. And we assume, as I mentioned, the trivial equilibrium. If there are no external forces present, no motion, no, manipulating of the string, then the string has a horizontal position. And here we're doing a very slight vibration. It's not a huge vibration. So it's very slight enough that we can replace the arc length with X, the horizontal position. So, so now we have our variable U that measures the vertical displacement as a function of X, the physical position, the horizontal position along the imaginary trivial equilibrium of the string, and T in time. So as it vibrates, as time is moving. And as I mentioned before, there's no transverse force, there's no stretching of the string or shrinking of the string, no transverse forces. There's no twisting, there's no torque. And the horizontal component of our tensile force is assumed to be constant. So that's how our model works. We balance the forces. In the horizontal direction, we assume the forces are perfectly balanced. In the vertical direction, we have to balance the forces there. And so, we use mass times acceleration to calculate the force. On the one side, we had mass times acceleration. And on the other side, we had all these other forces, such as So here we have the vertical acceleration of the string. On the other side, we have this term, which is interpreted as a restoring force due to the string. And then we could also have gravity and some other external force. Here, I don't know if force is necessarily the right word to use. Here, it did have mass multiplied to this, and we canceled the mass on all sides. But yeah, so there's just the external, data. And here, this c squared is really what I want to talk about today. Why do we, so if you go back to the derivation, we can show c squared is t sub 0 over rho naught. Rho naught is the linear mass density. So we can show c squared is the tensile force divided by the density times the cross-sectional area. And it's positive, but I want to show you an interpretation. Why did we set this equal to c squared, and what exactly is c? Okay, so that's part of what I want to talk about today. So for our most simplest idealized case that we're trying to solve the problem, we're going to assume that g is 0 and f of xt is 0. From a purely mathematical point of view, if we don't do that, then our PDE is not going to be linear. And we're not going to have the set of functions that satisfy the PDE form a vector space. So from a purely technical point of view, if we don't zero those out, separation of variables doesn't work, which would be a huge bummer. So yeah, again, we'll talk about when you do have these other forces, how do we deal with that? And so we have these nice fixed boundary conditions here at the ends, and certainly that can be changed. We're just going to, do this slowly in baby steps. So one traditional problem is where one end is fixed and the other end is moving up and down, and we'll work up to that. And then we have our initial conditions here are slightly different from the heat equation. For the heat equation, we had an initial temperature of the rod. For the wave equation, we have an initial position of the string. So for example, we could have, if we said u of x comma 0 is 0, you could have a trivial position, like the string is just horizontal, or perhaps I could pluck the string. I could just hold the string for a second, pull the string up right here near the center or wherever and hold it for a second. Then that shape, is a function of x. That would be your initial position. The other possible parameter is the initial velocity of the string. So here I could strike the string, or I could pluck it, hold it for a second and let it go, right? Or I could strike it. If I'm striking it, I'm not only giving it an initial position, I'm deforming the string, but I'm also imparting an initial velocity to the string. So instead of initial temperature, we have initial position of the string and initial velocity of the string. And those are initial conditions. So in particular, that's information given when we've plugged in a constant value for the t variable, initial condition, as opposed to boundary condition, where we've plugged in constant values for the x variable, right? So in general, as with, the heat equation, if we don't have a vector space structure for the PDE and boundary condition, we will assume u of xt has this, this kind of structure where we have a u bar of x, a part of the solution that's not dependent on time. So that's what happens when t goes to infinity, and a transient solution that is dependent on both x and t. Of course, if the PDE and boundary conditions already form a vector space, you can go to separation of variables directly. Okay, but in general, we would make this assumption if we didn't know that, we had that vector space thing going. So that much, so there's not a lot different here. I would say that the main difference thus far is this is one more partial. Our heat equation is just, if this wasn't a second partial here, let me get rid of this. If this was just a first partial, then the PDE looks identical to the heat equation. And the other part that's different is we have this potential, second initial condition here. With the heat equation, we typically only had one initial condition, right? The initial temperature distribution. But again, maybe there's room even in the heat equation to make that more complicated. For the online exam, you're going to use your own paper. So a student was asking about blue books. For the online exam, you're just going to use your own paper. And yeah, and then I'll make the exam available to you, and then you'll take the exam and upload it to Gradescope. And then there's no class on Friday after the next day. Woohoo! I'll be grading, so no woohoo. So yeah, I wanted to do a little example here and do a steady state calculation. And, we did a lot of theory. Let's do some math. So here's I want to look at this form of the wave equation where we have gravity, but there's no external force. Okay, so just the string with gravity. Okay, and usual ends tied. Here, since time will not be a factor, we don't care about the initial condition. All right, so as with all the steady state position now, in this case, right, not steady state temperature, or steady state position, because U is the vertical displacement, of the string. So as always, we now assume U does not depend on T. I assume U is not a function of T. So if you take the first or second derivative of U with respect to T, you're going to get 0. So here, I'm going to replace U of xt with U bar of x. Since it's not a function of T, the second partial with respect to T is 0. So this left-hand side here zeroes out. And so I just have the right-hand side equal to 0, and I've replaced this second partial of U with respect to x. I've just replaced it with a second derivative. And here, this term we zeroed out. So now I'm going to isolate the U bar double prime term. I move the minus G over. It becomes positive. And then multiply both sides by rho naught, divide by T naught, and integrate once. So there's the G that we moved over. It's positive. We multiplied both sides by rho naught, divided both sides by T sub 0. Integrated once, you get the x plus a from the integration. You get the variable plus your, constant of integration. Integrate one more time. Integral of x is x squared over 2. Integral of a is just ax, and then plus another constant of integration. So now we need to use the boundary conditions. We have two unknowns here. This is a second order ODE. So we ended up with two unknowns here. So we use the boundary conditions. If we let x equal 0, so for this first boundary condition, we're going to let x equal 0. So this term and this term completely zero out. So here, these terms are gone. And we're setting this whole thing equal to 0. So we get b equals 0. So that's what I have here. So if you go back to the solution, this term at the end is no longer here. U bar of x now just looks like, rho naught times g over 2 t sub 0 x squared plus ax. So let's see, there's a question. So the reason we make the assumption that partial u partial t equals 0, so we're assuming u is not dependent on time. We're trying to see what's the time independent part of this system look like. So similar to the equilibrium temperature idea, we have this idea of there's, when t goes to infinity, maybe it'll have some kind of rest position. So the assumption we're making is actually right here. It's that u doesn't depend on t. So this is the assumption. And then everything comes from that. So then I know the first derivative is 0. So the second derivative is 0. But it's to kind of find that time independent equilibrium resting temperature. Here it's not temperature, it's position. So now if we let x equal L, so now that's in here now, I'm letting this x right here equal L. And remember, the b term was 0, so this b term's not here. And we're setting this whole thing equal to 0. And I want to solve for a. So there's a L right here for the x and a L squared right here. And we want to solve for a. So divide both sides by L to get, to isolate a. So I can divide both sides by L, that goes away. That becomes an L. And then move this entire term to the other side. It becomes negative. We get a is equal to negative rho naught g over 2 times t sub 0 times L. So what we've found now is this coefficient right here, a. We know b is 0, so there's no b term. So we have, if I plug in a, I've got the steady state position. So now let's do one very important thing. Here, I'm going to factor out the common terms. And I'm going to think about the graph. Think about the graph. So here, this is second order, so it's a parabola. It's a parabola where the height, the y value is 0 when x equals 0, and it's 0 when x equals L. So just like a Calc 1, let me just Calc 1 style draw a parabola. Here's 0. Here's L. This is an upward facing parabola that goes through the points 0 and L. That's its resting position. So you can see it's sagging. So what's up with the sag? Well, we can figure out the lowest point just by taking the derivative and setting it equal to 0. Take the derivative, set it equal to 0, solve for x, the critical point. Do you remember all your Calc 1? The critical point is right in the center. So at the center, you have the lowest point of the string, and this is the actual, height of the string. You see the minus sign there. And so this is a natural sag that we would expect in a string, if you're in a gravity environment. If you're in a gravity environment, of course, it may not be that pronounced. I drew a very deep sag there. But once you introduce gravity into the system and solve for the steady state, we get a resting position that seems to match our intuition. All things left alone, you pluck the string, eventually after it's done vibrating, you expect it just to be done, just be sitting at its resting position. If gravity is involved, there'll be some amount of sag. And here, because it's equally supported on either end, we expect the center to be that low point. So, and you never thought of just a string sitting there with a sag in the center was so complicated, right? But this little example, it's kind of confirming, okay, at least the math is behaving a little bit like we want it to. It's mimicking reality a little bit. Okay, so think about this example beyond just the math, that when we, at the end, we actually calculate the resting shape, and we can mathematically show that there's, you know, a sag, and you see all the other factors that are involved in how much that sagging happens. The tension is involved, and look what happens if you make the tension larger. If I increase the tension, the overall term gets smaller, it gets closer to zero. There's less sag if you increase the tension, you know. So if you decrease the tension, there's more sag. You know, if you change the density, that'll affect the sag. So this is good in that it's behaving like how we'd expect. You know, in reality, it's acting like our intuition. Okay, so finally here, let me do some quick and non-rigorous analysis of this c squared term. So in our wave equation, we have this term c squared, which is T naught over rho naught. T naught is the horizontal tensile force, the tension, and rho naught is the linear mass density. Okay, so let's figure out what the heck is C by doing a very simple, you know, unit analysis. So the force, as you know, is mass times acceleration. Okay, so here, acceleration is, the units here, length divided by time squared, right? You know, miles per second squared, right? That's acceleration. So here it's length per time squared. Rho naught is our linear density. What do I mean by linear density? That's mass per length. Okay, rho naught is our linear density, mass per length. And so now let's plug in these units and see what are the units of C. So remember, C squared is equal to T naught over rho naught. T naught over rho naught is positive. So here I take a square root, and I'm keeping only the positive root here. So T naught I replace, so T naught here, that's mass times length per time squared. Rho naught, I'm dividing by rho naught. Rho naught is mass per length. So if I'm dividing, that's the same as multiplying by the reciprocal. So here is the reciprocal of rho naught, right? The linear density is mass per length. I'm dividing by mass per length, so that's the same as multiplying by length divided by mass. So what happens now, if you'll notice, the mass term cancels. The mass term cancels. I have length times length in the numerator. So I get the positive square root of length squared over time squared here. This is the absolute value of the length over time. Length over time, you know, like meters per second, that's velocity. The absolute value of velocity is speed. So here, if we look at the units for C, we get what seems to line up with units for speed. And so we conclude that C is some sort of speed related to a vibrating string. So this is the part where you have to now think about your own physical intuition. You know, in your mind now, you're vibrating a string. And you're thinking, what's happening as that string vibrates? Okay, so here, there's a question here that says, at what speed do signals propagate along the string? So to me, for a person that's not very like physical, you know, I'm more from the point of view of understanding the model, I'm more in the math. To me, this question presupposes that there is a signal that's propagating along the string. I kind of buy it. If you think about a string that's vibrating, there's kind of, it seems like there's something that goes back and forth. Right? So we'll call it a signal that's propagating along the string. I mean, I guess when you're sending Morse code or whatever, that's a vibration that you're propagating along the string. It's a signal you're sending along the string, right? So Morse code, you know. So here we conclude that, you know, in the whole system, in our wave equation, the only place where there is a speed, other than that initial velocity, is this parameter c. So we make this conclusion that c is this so-called propagation speed of some signal when you pluck the string. And so now another question we can ask: how much time will it take for the signal to travel from one end of the string to the other? So you pluck it, and now you imagine the string is vibrating up and down, and there's this string, this kind of signal that's propagating back and forth, you know, that's because of the vibration or causing the vibration. So here you remember from Calc 1 that distance equals rate times time. So that's, you know, that's the old, super old school. You remember one of our first formulas we ever learned in physics and calculus, and it changed our lives forever. Distance is rate times time. I'm looking for time. So time is distance over rate. The distance traveled here. So I want, the distance would be from one end of the string to the other. So go one end of the string, it'll travel the distance of L, and then back is another distance of L. And the rate here, I'm going to use this speed C. So here, the time, so for time, I'll use the letter tau. So here, tau, T for time. Okay. The time, I do distance over rate. So here, L is the distance over rate. That's going from, you know, maybe the left to the right, and then from the right back to the left. So going to, you know, to and back. So we conclude that the time required for the signal to propagate from one end to the other would be 2L over C, where C is, you know, something that's dependent on the tension and the density here. Remember, C is a function of that tension of the string, the horizontal tension, how tightly we've tied the string to the two ends, as well as the material of the string is involved. Okay. You know, you could think of a string that's made out of nylon versus a string that's made out of rope versus a string that's made out of, you know, steel or some metal, you know, and then plucking those, vibrating those, or a string that's made out of hair or gut, right? Some of these instruments use string that's made out of like lining from an animal's gut. So yeah, this is not any rigorous analysis. This is just trying to physically get some kind of intuition for what's going on with all of these equations. So we're not just pushing around symbols, even though at the end of the day, that's a lot of what we're doing, but we'd like to be thoughtful and think, okay, what are the physical ramifications here? So Evan.
Yeah, I had a question. So when you referred, so C is a constant of speed, but we also know that none of the points on the string are moving horizontally.
Yeah.
So in this case, C would be the rate at which the waves themselves are moving along the string.
You tell me. It's a signal propagating along the string. When you pluck a string, you know, when you do the thing where you have a string in the two tin cans, and you stretch the string really tight and one person talks on the other end, and that the sound, you can hear them on the other end. To me, that's a vibration. That's a very subtle vibration. And there's some kind of signal, I guess, that propagates to the other end, because the person on the other end is like, hello, yes, Edison, I can hear you. I mean, they didn't use tin cans, but so yeah, there's some kind of energy propagating along the string when you pluck it, you know, and this is the speed of that signal propagation. So good question, Evan. This is that physical part where, you know, at this point, I tell everybody to go home and tie a string between 2 points and start plucking it, you know, or if you happen to be a musician and have a guitar or violin or whatever your favorite stringed instrument, you know, something with tension, you know, that'll vibrate. So yeah, good question. And we'll just keep thinking about it. I will not give you a lot of satisfying answers. Unfortunately, I am still working on mastering the secrets of the universe, but once I do, I will send you an email. So about 10 to 15 years, expect an email from me. So another question we ask is, what's the natural frequency of the oscillating string? So frequency is the number of cycles per given unit of time, you know. So I'll let you think about what frequency means. So here, assuming the time is what we calculated, distance over rate, where the distance is 2 and back, so 2L over C. Assuming that's the time, let's try and make a frequency calculation. Let's try and calculate the frequency and see what we get. So it's the number of cycles over time. I'm just going to assume the number of cycles is just some constant. And dividing by time is the same as multiplying by the reciprocal. So here, the frequency is some constant, and then you divide it by time, that's the same as multiplying by C over 2L. Okay, now let me just plug in here for C. Let me move the 2 over. I don't really need it. I'm going to move the 2 over under the constant. And let me plug in for the actual definition of C, because I want to connect this back up to our physical intuition and interpretation of what's happening. So I have it written as a constant over 2. That's right here. Constant over 2. There's the 1 over L. And then there's the C term, which I've put in the definition for the C term. So finally here, I can replace rho naught, which is the linear mass density, with delta. So this is the density that's mass per volume. So delta here, this is mass, oh my OMG, per volume. And A is area. So if you multiply the mass per volume by area, you get the linear density, which we were calling rho. Okay. All right. That's my writing for the day. Okay, folks. So what was the point of all this? Finally, here's the point. You've been so patient. All right. If you have a guitar or something, get it out. It's go time. So let's think about now, if we mess with these parameters here on the right-hand side, how will that affect the frequency? Okay, so here now, suppose we decrease the length. So here, suppose we make L smaller. If you make L smaller, 1 over L gets bigger, the frequency increases. So by decreasing the length, so on a guitar, this is like using a capo. So do y'all know what a capo is? So on a guitar, if they want to artificially shorten the length of the neck, it's a clamp basically, and it comes down. I don't play instruments. I don't play any musical instruments, but I played one and I play once. No, I'm kidding. You've seen people play. So yeah, so a capo will cause that increase in pitch, or even if you just clamp the strings down closer to the bass, I guess. I have no idea. Who am I, Jimi Hendrix? If we increase the tension, so now, we're doing some basic algebra here. So if you make T sub 0 bigger, that makes this whole term bigger. The frequency is going to increase. So here on a musical instrument, on a guitar, this is if you tighten the strings, that'll increase the pitch. And here, what we're observing here is the math is behaving like our intuition. That's what's really remarkable here. We can't take it for granted that the equations, the model we put together is going to act like reality. So here we're kind of confirming, okay, we're getting some, convergence between reality and our intuition and our math here. So let's look at this density term. If we increase the density, so look, since it's in the denominator, if you make the denominator bigger, the entire fraction gets smaller. That decreases the frequency. So here, you compare steel strings versus nylon strings. Okay, so one of these strings is denser and will give us a different sound. So this part I have no idea. So if there's anyone who plays guitar or something who wants to chime in, feel free. So steel strings, presumably decreases the pitch? I have no idea. I guess nylon strings make sense in my mind that nylon strings would have a higher sound when you pluck it. I don't know why, but it does. I do know why. It's from, I used to play tennis and I used to kind of pluck on the strings of the tennis racket. And I know how a nylon, kind of tennis, anyway, too much information. So used to bad ankles, stop playing. Okay, anywho, what if we increase the area, the cross-sectional area? So here, A is in the denominator. If we increase the area, it makes the whole fraction smaller. The frequency will decrease. So this will decrease the pitch, apparently. And again, now I have no idea, but apparently there's wound strings, which are thicker versus solid strings. The wound strings are literally one string they've got a string and then they've wound that string with another string. Again, I'm not an expert on any of this, so if anyone wants to chime in, please let me know. Give us a music lesson, whatever. So yeah, so at least mathematically, we can show here that pitch should decrease, and I guess that fits with our intuition. Finally, how does gravity affect the frequency of the vibration? Without any math, it's hard to answer the question, but based on the math, nylon strings usually sound softer than steel. Nice. See, at this point, we should start playing some musical instruments. So yeah, so people are confirming some of these things. Some of the musicians in the audience are confirming. I guess you can also read the chat. I left it to everyone to facilitate group formations. Okay. Yeah, so that's right, Evan. Gravity doesn't affect the model according to our analysis, according to this analysis. We probably have to physically do some experiments. So yeah, since G does not appear in the formula, it doesn't seem to affect the frequency. And the tensile strength is measured by a constant known as Young's modulus, which doesn't appear here and apparently also does not affect frequency. So here's some variations of the wave equation. We talked about this last time. So we're adding terms, for example, for stiffness. And so this is an added term for stiffness. And this is Young's modulus that takes into account the stiffness, and the R squared is takes into account the radius. So this is for damped motion. So this term, it's like if you pluck a string and then put your finger on it, damped motion. And we'll talk about damped motion some more and why that term appears. Suppose you're hitting a drum. So this is the 2D. So now the only difference is now here I have X and Y. Just like for the heat equation, we talked about the 2D and 3D version. We're kind of now exploring that, in your mind, you should, we can take this to higher dimensions, obviously, right? 2D, 3D. And so here, this term, we can look at the two-dimensional version there in X and Y, the two spatial dimensions to model maybe a drum, for example. And finally, for a longitudinal vibration, so let me talk about this. Here, be careful. This is V. And so longitudinal, we mean, to the left and right, motion along the string. So here in our original model, U, the letter U was the vertical height, but V here was the horizontal displacement. Because if you really think about it, there's only one point that's moving vertically up. That's the point at the center of the string. Every other point is going to have a subtle arc to it. And so V is that horizontal motion. And apparently this is a model for V. And, I don't know where this model came from. Certainly there's, a lot of models out there. And I told you model building is a real art. Like to me, that's the ultimate, to be able to just go, okay, here's a physical situation. Let me think about it and write down a simple model, So you know those sound canceling headphones by Bose? I think ultimately that's Bose's strength, right? So Bose is, I think he's from Bangladesh or wherever, he's an engineer. But Bose was on an airplane and got this idea for the sound canceling headphones, and very quickly just sketched out just wrote down the model, I believe, just made a rough sketch, and then gave that to the engineers. And then it took them 2 or 3 years to go from there to the actual product. And this was years ago. So, you know, those headphones came out years ago. And then after that, now you've got all these other headphones that have come out. So yeah, being able to create these models, that to me is a real art. Okay, so that ends that discussion of properties of a stretched string. Next, after that prelude, you know, we actually want to start doing some math and get down to the business at hand, which is solve a wave equation. So now we're back in the book, section 4.4. And this is just, you know, to remind you of the situation. So we already saw this. So here, let's do math. Let's for a second step away from the physical ramifications. And now let's think about the mathematical ramifications. Okay. So here's the PDE. Again, take some time. You know, PDEs is tough. Just understanding the question requires a sophisticated amount of mathematical knowledge. That's how tricky PDE is, just to be able to read a PDE problem, right? So there's our, you know, things, there's our PDE, and, you know, think about the domain. And then we've got, as always, we've got our boundary conditions. Think about boundary conditions, what that actually means, versus our initial conditions. And here, this is different from heat equation. We have the potentially we have two initial conditions, the initial position, initial velocity. And then of course, the wave equation is different in that on the left-hand side, we have a second derivative with respect to t, not just a first derivative, as in the heat equation. So yeah, so what's not different is we will use separation of variables again. And so, of course, for separation of variables, you know, the whole idea for separation of variables and what makes it work is when we use separation of variables, we end up getting more than one solution, and we really need the vector space structure to be able to put everything back together. You know, this separation of variables allows us to take everything apart, but it's the superposition principle that allows us to put everything back together. And so that's why we need a vector space. And so you can even almost think of this kind of as review, because this is the fundamental theory that, you know, underlies solving the heat equation as well, right? That we need the vector space structure. And here I wanted to do it a more kind of, here's maybe you'd see, we would pose this kind of problem maybe in a linear algebra class. Here, what we'd like to show is W, where W is this function u of xt defined on this domain, you know, x between 0 and L, t greater than 0, where W consists of all functions that satisfy the wave equation and that have that have these boundary conditions. So fixed ends, is, you know, trivial fixed ends. So that's the PDE and boundary condition, and we want to show this forms a vector space. So I want to show this forms a vector space. And so what does that mean now? So that's the question I always want you to ask yourself. Okay, what does it mean to show something as a vector space? So now what I want to do is pick two elements in W and let U3 be the sum. So I want to show now, if you take two elements in W, add them together, that new function that we created will also be in W. Okay, so here I've added U1 and U2. And so its domain will be the domain, you know, 0 to L and t greater than 0. And now if I take the second partial of this new function with respect to t, you know what happens with the linearity. So here's U sub 3, but then I replace it, and we know the derivative is linear, so I can distribute the partial to each term. And now each function here, U1 and U2 individually satisfy the wave equation. So each one of those is equal to, you know, the other side of the wave equation, c squared, the second partial of u with respect to x. And now we pull that second partial with respect to x out, again, using the linearity, and then replace, you know, U1 plus U2 with U3 here. So U3 satisfies the wave equation. You know, if U1 and U2 satisfy the equation, then the sum satisfies. And here for the boundary conditions, we can show U3 satisfies the boundary conditions. And so if you take two elements in W, add them together, they'll still be in W. And then here I show scalar multiple is back in there. I used alpha for my scalar instead of C. I used alpha, I don't know why. Pick a function in W. And again, I'm taking the second partial of alpha U with respect to T, using the linearity, pull out the alpha. U is in W, so the second partial of U with respect to T, that equals, you know, the other side of the heat equation. And then put the alpha back inside. Again, using linearity, we can put the alpha back inside. We put the alpha all the way in here. And so we get our you know, other side of the wave equation. And again, you can very easily and quickly check the boundary conditions are satisfied. So if U is in there, then a scalar multiple of U is in there. If U1 and U2 are in there, then the sum U1 plus U2 is in there. So by closure properties, W is a vector space. We've shown it's a vector subspace. So the next thing, we are now cleared for takeoff for doing separation of variables. But this is my time, so I'm going to stop right here, and we'll do separation of variables on the wave equation next time. And you know, that'll be a good review of separation of variables. Okay, and this is how it'll go for a little bit. Actually, for the rest of it, we'll talk about Laplace's equation, and we'll solve that with separation of variables. We'll do the two-dimensional version of Laplace's equation. We'll also look at Laplace's equation on polar coordinates. But it's all, you know, separation of variables. Oh, so let me stop here, and I thank you all for your time.